Good afternoon, ladies and gentlemen. It's my pleasure to welcome Marco Bresciani from the University of Erlangen as a speaker of today's seminar. So Marco got his PhD in 2022 from the Technical University of Vienna. So his advisor was Elisa Davoli, and then afterwards he moved to Erlangen to the group of Manuel Friedrich, where he is now as a Humboldt Fellow. So he got a Humboldt Fellowship. So you can see it from his slide. So Marco also received the Klaus Kerper Prize from the GAM Society, German Society for Applied Mathematics and Mechanics, last year, I think, for outstanding young researchers in the area of applied mathematics. And quite recently, 2 weeks ago, he got the Junior Award of the ISIM, so International Society of Interaction between Mathematics and Mechanics, which is devoted to young scientists working in the area of mathematical applications to mechanics. So, and today he will speak about his variational model of Eulerian-Lagrangian formulation with material failure.
So, thank you very much, Martin. I'm always happy to come whenever the chance to visit you in Prague. I want to apologize because I was supposed to give this talk here last November. I was scheduled a visit here, and unfortunately I got sick, so I had to cancel. I'm very sorry for that, but I was not in the condition of traveling, and I'll try to make it up today. However, I'm worried that Martin may have raised too much the expectation from. I was saying I'm afraid that Martin may have raised too much expectation for my talk. I don't want to disappoint you. So, as the title says, I'm going to speak about variational models with Eulerian-Lagrangian formulation, and I want to include this has been a very active topic of research in the last years, and the plan here was to include material failure into the picture. And all I'm going to present today is based on joint work with Manuel Friedrich, who is my mentor at FAU, and Carlos Moracoral for the Università Autónoma de Madrid. So the outline of the talk is going to be very simple. I'm going first to describe what I mean by Eulerian-Lagrangian energies, and subsequently we will investigate two settings. The first one, when we allow material failure in the sense of cavitation. As a terminology here, I refer to the terminology by John Ball. So when I speak about cavitation, I refer to the abrupt formation of voids inside of solids in response of mechanical stresses. And lastly, I would like to mention briefly some results instead in the direction of fracture. So by Eulerian-Lagrangian formulation appear in many fields of multi-physics problems. And the idea is an energy when I couple nonlinear elasticity with other effects. So we investigate energy, which are a function of two variables, y and v. Y is a deformation defined on the reference configuration of an elastic body omega, and he has to fulfill the standard assumption of continuum mechanics. So it has to be orientation preserving and injective in order to exclude the interpenetration of matter. And instead, then the second variable v is what I will generally refer as an Eulerian field. It's an Eulerian field because its domain of definition is y of omega. So it's a deformed configuration in the actual space. So this is the characteristic feature of this model, and actually the main source of difficulties for the analysis. That's even clear because y of omega is going to be one of the unknowns of the problem. So let's look at the prototype of energy that we have in mind. As I said, the energy is a function of y and v. We have first an elastic energy term. So W is a non-convex elastic energy density, which depends on the deformation gradient, and also on V evaluated in the reference configuration. So it's a Lagrangian term that is an integral of omega. The second term instead is the Dirichlet energy of V, which is defined as an integral over y of omega. So on the unknown deformed configuration in the actual space. Just a quick note or notation, I use x for the variable in the reference and psi for the variable in the actual space. in order to include in our analysis other models available in the literature, I also we'll also consider the case in which B is allowed to jump. And so in this case, what we also consider this term here, which is just the measure, the n-1 dimensional houses of measures of the set J of B, which is the set of jump points of B. And plus lower order terms, which depends on the specific model under consideration. But to make my discussion more concrete, I would like to mention a few instances that fall into this prototype energy. The first one is the theory of liquid crystals, and in which B can be thought to be the nematic director. And this corresponds to the Frank-Ozen energy in the one-parameter approximation. And in this case, B has to fulfill the sphere value constraint. Another case is the theory of phase transition with the Eulerian interfaces by Shilavi. And we can think of V as a phase indicator for M species of a body, so that the sum, if we think about BI as a concentration, the sum is equal to 1. And this is a case for which the fact of allowing B to jump could describe, for example, sharp interface models. While when we exclude jumps of B, we are thinking about the diffuse interface model. And the last example that I want to mention, which is the one that I came from, is the one of magnetoelasticity. In the case B, denotes the magnetization field, which is defined on the actual space, on the form configuration, and has to fulfill this constraint, given by the fact that I interpret B as the density of magnetic dipole per unit mass and not per unit volume. So this is just the Jacobi determinant of the inverse. But if you want to do some math, there are a few issues that are evident already at the modeling stage. For example, again, we have Y as information defined on omega, and V an Eulerian field defined on Y of omega. So we have an energy such that the domain of one of the integral is one of the unknown factor. But in particular, if you consider the formation with low regularity, the question arises how to interpret this set here. For example, if you think about Sobolev function or SBP function, these are functions that are defined just almost everywhere. So this is a very delicate issue because we know, for example, that if I have two representatives of a deformation, so two functions that coincide almost everywhere, their image can differ by a set of positive measure. Let's take for the famous example by Poincaré. And also, all the terms here are quite delicate because also this composition here may be undefined on a set of positive measure if Y doesn't satisfy what is called the losing condition n-1. And also, and it's really a crucial point here, suppose that if Y of omega is not an open set, how can we define this gradient here? Because we know distribution on derivatives can be defined just on open sets. So we have to find a good replacement for Y of omega, which is an open set. And overall, the question here is how we can define all these objects in such a way that the value of this energy functional is independent and representative. So here we have to be very careful because behavior on sets of measure 0 really matters. Okay. As I said, I will consider two cases. The first one is is a possible theory allowing for cavitation. So here, the formation are meant to be are modeled as Sobolev mappings, but we need to impose subcritical coercivity assumptions, subcritical integrability, because we know that if the integrability exponent p is greater than n, the formation are continuous, and so we won't see cavitation appear. Here, I'm very sorry, this slide is very full, but just the only one is going to be so packed, but I need to introduce some terminology. And we'll fix a scaling P, which is strictly greater than n, the space dimension -1. It'll be clear later the meaning of this condition. And I consider as a class of admissible deformation maps in W1P, which are Jacobian determinant in N1. For obvious reason, this to be positive almost everywhere. In particular, I need to impose injectivity. The usual assumption is injectivity almost everywhere. Here I need a little bit more, which is this condition IMP. So condition IMP has been introduced by Müller and Spector, is linked to the topological degree. I don't want to be too technical in here. Let me just say that condition IMPs exclude the following fact, that a cavity created at one point can be filled from material coming from elsewhere. And in particular, the formation satisfying him are injectile out of set to measure 0. So this falls in the setting that I described before. And all the analyses here are based on the interplane between two concepts, two possible formulation of image, which is the geometric image and the topological image. The first one is the geometric image, which I denote by E, and is defined as follows. I take a subset of omega, which is the set of points where y at the same time has singular behavior in the sense of geometric measure theory, and I call it as the geometric domain. And the geometric image is nothing but the image of this set. So the geometric image, what is this? Is the image of a subset of omega of full measure. And the main feature of this set is that it's not generally open, it's just a rectifiable subset. And actually, its definition depends on the representative. So if I take two deformations that coincide almost everywhere, these two sets can be different. And the second notion that I need is the one of topological image, denoted by int t. And here the definition is a bit more technical. Let me explain. So suppose that I take a subdomain U well contained omega. And if the restriction of y on the boundary of this, it's W1P, given the fact that P is chosen to be strictly bigger than n-1, by Mori embedding, I have that the restriction of y on the boundary of this set is a continuous function. Yeah, I need this star because I take the precise representative, but basically the restriction of y on the boundary of U is a continuous function. In this case, I have a very powerful tool, which comes from topology, which is the degree. And I can define the topological image of U under Y as the set of points with non-zero topological degree. Roughly speaking, I take the image of the boundary of U, and whatever is enclosed inside this curve is the topological image. And then I can define topological image of omega by taking the union of all topological images of the subset U as a graph. And the nice feature of this set is that this set is always open by the continuity of the degree and is actually independent of it. Last definition that I need to give you is the one of cavity. What do we mean by a cavity? By a cavity, we define it as follows. So suppose that we take a point A in omega, and we do the following. We take all good set U as above, such that Y is continuous, the restriction of Y on the boundary is continuous. We make the topological image, we take the closure, and then we take the intersection among all subset U. So in most of the case, I'm going to end up with a single point, which is Y of A. But if the deformation opens a cavity at A, I'm going to see that this set here has positive measure. Okay, let's make a picture in order to make this clear. Here I depicted a very pathological deformation. So omega is a square, and this deformation has some singularities. For example, is compressing this segment here, this black segment here, in this bottleneck here. And also you're opening a few cavities. For example, this cavity is opening here, here the other one, two cavities here. So it's a bit hard to orientate this. Two cavities here are open there. And I have also this segment here, which is obtained by opening a cavity and squashing it onto a set of measure 0. And so let me point out that you can have various singularities, like cavities can touch the boundary, cavities can touch by themselves, and so on. So if I take U, a board that surrounds this point here where the cavity is open, the topological image is not going to be nothing but whatever is enclosed in this blue line. And if I do this for all the subset U, I end up with the whole thing. Okay, now instead for defining a cavity, let me go back to the previous case. So I have U, and what we do is a smaller and smaller set, such that at the end I end up with exactly the cavities. So we see that this defines properly the object that we have in mind. So the last ingredient that I need is the one of surface energy. Is this function that has been introduced by Nauer and Corral, denoted by S, in their study on the weak continuity of Jacobian, because here P is smaller than M, so we need to add something. If we don't penalize the creation of arbitrary amount of surface, we won't have the weak continuity of Jacobian. And this expression is not relevant to have a full justification of this. I can do some formal computation, but the right thing would be the theory of Cartesian current. Let me just say that, roughly speaking, this function here computes the surface of the boundary of Y minus the surface of the image of the boundary. That is the measure of the new surface created by the deformation. And what Enau and Moracoral proved here is that in this setting, if the surface is finite, I have the following. My deformation opens at most accountable number of cavities, and the surface energy is nothing but the perimeter of the cavities. Also, the topological image is nothing but the union of the geometric image and the union of the cavity up to set measure 0. Eventually, the reduced boundary of the geometric image inside the topological image is exactly the boundary of the cavities. That's exactly the picture we had in mind before. So the geometric image is what you see in gray. The topological image is what you see in gray plus the cavities. And what the meaning of the energy is exactly the perimeter of the new surface, which is the one depicted by blue. Here, since this curve does not enclose any volume, this is not a cavity. So it's just the blue curve that you see here. Okay, the first result that been for this problem exclude a priori the creation of cavities. So they are still in the realm of pure elasticity. This is modeled by imposing a priori that the surface energy is 0. Given what I just told you, this enforces the equality between the geometric and the topological image. So in this case, what they studied the following energy. The elastic energy is before, and then the gradient is rewritten, the gradient of V is rewritten just replacing Y of omega with the topological image. Indeed, since this is an open set, it doesn't depend on representative, I can think B just as a Sobolev map on this set. So the existence of minimizer has been proved by Enau and Moracoral in this paper here of 2017, while instead I extended the analysis to the quasi-static case. And lately, more recently, there's been some extension where deformation are allowed to belong to some only Sobolev spaces in these two recent papers. There are also other previous papers for continuous deformation. Also, in particular, I would like to mention this paper. Where is it here with Lisa and Martin? But and on which we pick up some techniques and we translate it in this more general setting. But here, if you want to allow concavitation, this is the setting we're going to consider. So Y is going to be an admissible deformation, and we take as B maps that are L2 on the geometric image, which are approximately differentiable almost everywhere. This is a pointwise notion of differentiability, which comes from measure theory, and allows us to give a meaning to this gradient here. And the energy that we consider is the following: is elastic energy as before. We have two parameters, lambda and mu. Lambda multiplies the surface energy. Then we have the gradient, is now V squared, plus the length of the jump of V inside of the topological image. Let me point out that on V, we take standard assumptions. We have growth condition just from below, P growth for the gradient, and some volumetric term in the determinant, which explodes as under extreme compression and is superlinear at infinity. And we also assume polyconvexity. Here I'm emphatic just the vector of all minors. So we can resort on the classical theory Bible and so on. I would like to point out that the factor restricting to the topological image here, the jump of V, allows to exclude the fictitious jump that may arise by self-contact at the boundary. Here I have a deformation. We take this rectangle here and deform it into an annuli. In order to have JV to be independent or representative, I have to define it as a subset of point of density 1 with respect to the geometric image. And this forces the case that if V are as the blue arrows as above, this red line here counts as point in the jump set. So the fact of intersecting with the topological image tells me that I'm not accounting for these artificial jumps. Okay. And the first result that we have about existence is the following. So the energy is as above, and up to this condition on the two parameters lambda and mu, so lambda strictly greater than mu, and they have to be both strictly positive, I have the existence of minimizer for this energy here, with the additional regularity assumption that this V tilde, which is nothing but the extension, I take V, which is defined on the new geometric image, and then define it to be 0 on the cavities. This function here has to belong to the space GSBV2. This is the space of generalized function of generalized special function of bounded variation. Just think about SPV. And it's GSBV2 on the topological image. So a few words. So this regularity requirement here is not for free. I have to impose it because, unfortunately, for the way that the cavities are defined, I don't have any regularity of these objects. So there is no way I can obtain this for free. And the second comment that I want to make is about these scalings here. This comes from the fact that from what we are able to prove is the lower semi-continuity of this term on this term and on the sum of the surface term and on the jump. So this term by itself, they are not lower semi-continuous, but their sum is, that's why we have this restriction on the scalings. And the question now would be, okay, but can I restrict to the case when V are not allowed to jump, as in some models, for example, of magnetoelasticity? Well, I can do it up to a certain extent. The model is the same as before. Let me assume that lambda is a positive, it's just positive, I don't have mu anymore. And then there exists a minimizer for this function here, which is the same as before, under the assumption that the extension V, V tilde, the extension of V by 0 inside the cavity, is a Sobolev function, belongs to W12. And the idea here is that this assumption is basically enforcing V to be 0 on the boundary of cavities. For some models, this could be still compatible with the structural assumption, but for some others not. For example, let me mention, as I did in the first slide, the modeling of pneumatic elastomers, where V is subjected to the speed values constraint. So this means that V tilde has to be 1 on geometric image and 0 in the cavities. So necessarily jumps on the boundary of the cavities. So this means that the class of admissible states is going to be empty in this case. So how can we solve this? Well, what we can do, we can proceed by imposing an a priori bound on the number of the cavities. So we assume that the total number of cavities that the deformation can open is at most some integer value m. So in this case, we need to introduce a further notion of image, which we call material image denoted by in m. And this is nothing but the topological image of y, so everything, minus the image of the cavities. So let us assume that the number of cavities is finite. So for every cavity, this object here is a compact set, so this is a finite union of compact set. And as a result, the material image is an open set. And we can also show that this is independent and representative. On the result of Barchesi-Naumara-Corral, we also have that the material image coincides with geometric image up to set measure 0. So this is a natural candidate as a deformed set. However, the resulting class of admissible states is not closed. We need a further restriction. And the restriction is posed in the form of a lower bound on the cavity's volume. For example, we fix some scaling kappa, and we consider all admissible deformation is below, such that if it opens a cavity, the cavity volume needs to be at least kappa. And this gives, by this parametric inequality, also an a priori bound on the number of cavities up to energy level. And up to this restriction, we're able to prove again the existence of minimizers by taking V to be a Sobolev map on this material image that I defined before. Unfortunately, this restriction of kappa is really needed because we have an explicit example. We show that if a cavity can squash, Sobolev regularity of the Eulerian fields cannot be preserved. Indeed, if I have that the cavity is closing towards the sequence, in the limit, this can experience jumps. And since this red line doesn't close any volume, the material image is going to coincide with the image, and V is going to be SBV on this set. So, and here I have a few ideas about the proof. Let me be very brief. One of the points is to study the continuity property of the topological image. What it turns out is that the topological image is not continuous, and what can go wrong is that cavities can escape infinity. So this is the reference configuration. The deformed configuration is going to be this dark gray area which encloses the surface. So this white square, sorry. And the topological image is going to be the union of the dark gray plus the white. And when cavities are approaching, we see that in the limit, the white part is not enclosed anymore. So the topological image is going to be just this dark gray part. As a result, we have a loss of math, which prevents the continuity of topological image, the convergence, sorry, of topological. And another point here that we need to use, but maybe here can be quick because it's a bit too technical, to prove the existence with the lower bound of cavities is the following property. So suppose that we have a convergent sequence of deformation. Whenever we have a compact set which is contained in the material image of the limit, this is contained in the material image of the sequence for n large enough. Here we have to put together many tools that they were already around. So the structure of the distributional determinant as a singular measure, as a measure with a singular part. And we have to put some fine properties on the reduced boundary and the boundary of the topological image, and about the monotonicity of the topological image. But let me, I just wanted to mention, just to give you an idea of the kind of mathematics that is behind this. And finally, I would like to present the result for the fracture case. Let me just tell you in advance that the existence theory here is not rich as the one we saw before, for the fundamental reason that SBV maps, they don't have any kind of continuity. They're essentially discontinuous. So in this case, we consider the formation SBV with an a priori infinity bound. So we put everything in a box and we assume them to be almost everywhere injective. In this case, the energy is the same as before, but the model requires control, of course, on the length of the jump of the deformation, and also requires regularization. We need to introduce this term here. So if you recall the meaning of, if you think about the perimeter of the deformed set as the union of the surface created by deformation plus the deformed boundary, we see that adding this term means nothing but penalizing the measure of the image of the boundary of the reference configuration, so of the pre-existing boundary. And in this framework, we can define geometric image and the surface energy as I showed before. And the result works as follows. So basically, we have existence for deformation y as before, SBV as before, and V with the additional regularity property such that the extension by 0, so V is the final geometric image. We define V bar as the extension by 0 of this map to the whole space, and this needs to have GSBV. Oh, this needs to have GSBV regularity.
Oh, no.
Thank you. And again, we have a restriction on the scaling given by the fact that what we're able to prove is just that the sum of this term plus this term is actually lower semi-continuous and not each term. And there is no hope to restrict to the case of where V is not allowed to jump. And the problem is that I can fracture two pieces of matter and putting them in contact together, as in this picture. So here I have a fracture which is open in this segment. And then what do? I consider a sequence deformation that makes them closer and closer. And when they touch, I'm going to have jumps of V in the limit. And here one technical point that I wanted to mention is the problem of the convergence composition, strong convergence. Let me just say that this is very delicate matter because usually composition are very hard to handle by variational methods. And what you've done here, you have to put this idea that was in my paper with Martin and Lisa into this framework, more measure theoretical framework, and to exploit Federer formula for the inverse, the convergence of geometric images, some results concerning injectivity everywhere of deformation, and put everything together. Okay, let me just sum up and conclude that we saw these are the first results that we have for Eulerian-Lagrangian energies for a framework that allows for material failure. We have seen two settings. The first one allowing for cavitation, where the formation are solid mappings. And this setting characterized by the interplay between topological and mesotropic motions. Eventually, I will show you the result from the fracture, where the analysis is quite limited by the fact that we have no topological degree in this setting. Two possible problems that arise at this point is the problem of relaxation. In these two for example, that I showed you, we don't have existence. The natural question would be, okay, I don't have a closed state space, but is this kind of behavior excluded by sequence, minimizing sequence? And can I still prove the existence of minimizers? If not, the natural question would be to relax and or rigorously prove the relaxation of this problem. And finally, another point would be to extend the result to the quasi-static case. And here, I think that should be doable, maybe a bit technical. We should have to put together the result for the quasi-static evolution cavitation with the results that I achieved myself for the problem of non-elasticity. Okay, I think I can stop here. So thank you very much for your attention.